So here we have several processes showing the work done. This is a kind of graph called a PV diagram because it plots pressure on the y-axis and volume on the x-axis. And because the work is the pressure times the change in volume, or if we have a changing pressure, it's the integral of pressure dV. It's simply the area underneath the curve on a PV diagram. So each of these has a different amount of work. In this first case, we follow the curved line from I to F. In this case, we follow another line where we start at constant pressure and a constant larger pressure until we get to the final volume and drop down. Notice in this case, we have a larger area, so a larger work. In this case, we drop to the lower pressure first and then increase the volume. So that's a smaller work. All three of these are positive work because the volume is increasing, so the system is pushing out on the environment, doing work on the environment. If we look for a moment over here at example E, here it's moving the other direction. So the work is negative. The environment is pushing in on our piston, making it get to a smaller volume. So the environment is doing work on our system. Example D illustrates two dramatically different cases. The green line has a very large work, large area underneath it. The red line has a very small work. And F illustrates when we go from the beginning, the initial, to the final, and then back to the initial. Even though we start and end at the same place, we went at a higher pressure going from initial to final than we did from final to initial. So even though we end up back where we started, the net work is still greater than zero. So a couple of things we noticed here. Work, as we've said before, is entirely dependent on the process. Different processes have very different amounts of work done depending on how we got from the initial to the final point. However, the quantity of heat transfer, the amount of thermal energy transferred because of temperature differences, also depends on the particular path we take for each one of these. But it turns out a certain combination of those two is not dependent on path. And that combination is delta E, the final internal energy minus the initial internal energy, equal to heat minus work. The heat minus the work, where heat is positive when it's added to the system, and work is positive when it is done by the system, meaning it's giving energy out to the outside. This is not dependent on the path at all. So we can define an internal energy based on this path-independent quantity. And this internal energy is then a state variable. So it just matters the initial and final points. And we can figure this one out just by subtraction. If we want to talk about this change in internal energy for very small amounts of energy, then we say dE internal is equal to dQ minus dW. A couple of comments. Because heat and work are both process variables, not state variables, they're associated with a process, not with the state that the system is in. We can't really call them true differentials. dQ is not, there is no heat variable that you're taking a differential of. So sometimes people like to put a small line through here to remind you that it only means small amount. It's not a differential. But for our purposes in physics, it still works perfectly fine. This is a small amount of thermal energy transfer, heat. This is a small amount of mechanical energy transfer, work. And this is the net change in internal energy. It is a true differential. Another thing I want to point out, This convention that work is positive when it's done by the system and negative when it's done on the system is not used by every single textbook. Chemists, in particular, really prefer to say work is positive when it's done on the system. That way both work and heat are positive when you're adding energy to the system. Because we're mostly interested in using this work done by the system to make an engine, we prefer to call work positive when it's done by the system. If someone is saying work is positive when it's done by the system, we would have a plus here instead of a minus. This is called the first law of thermodynamics, and it's essentially just a statement of conservation of energy. The total change in energy of a system is equal to the amount of energy you add through thermal means because of a temperature difference, known as heat, or through forces, known as work. A couple of comments. The internal energy of the system increases if thermal energy Q is transferred to the system and decreases if thermal energy Q is transferred from the system. Internal energy increases if work decreases if the system does work on its surroundings, and increases when there's a negative amount of work because that's work being done on the system by the surroundings.